So last section we said that we were going to talking about what this negative sign means on Faraday's law, and we get the meaning of that, the direction of it, from Lenz's law. It's negative because it means that it's going to happen in the opposite direction. And Lenz's law says that the current caused by the induced EMF travels in a direction that creates a magnetic field with flux opposing the change in the original flux of the circuit. Sometimes that will mean that the magnetic field from the induced current will be in the same direction, and sometimes not, and we're going to go through those situations. So what does Lenz's law mean? Well, here I have a magnet approaching a loop. So the magnetic field goes towards the south end of the magnet, and here we're moving a loop towards that south end of a magnet. That means that the magnetic field is going to the left, to the right, and getting stronger. So the magnetic field is increasing. Since the magnetic field is increasing, the magnetic flux is increasing. And so that means the induced EMF will want to tend to oppose that change. So that means the induced magnetic field is going to want to be opposite. Since the magnetic flux is getting stronger, it wants to make it weaker. To make it weaker, it needs to make a magnetic field in the opposite direction, which would be to the left if the original magnetic field is to the right and getting stronger. So that basically, if we have two vectors pointing in opposite directions, we have less of a vector. So if the magnetic field is to the left, we basically grab it with our fingers, right? So we grab it with our fingers on the inside. So I'm going to put my hand on the inside to grab it with my fingers. And I want to use my right hand. So if my right hand is in that ring, my thumb will be pointing that way. And that is in fact the direction of the current. So the induced current will oppose the change and then decrease the net magnetic field inside the ring. Doesn't matter what happens on the outside, just on the inside. Then, however, if the ring continues over the magnet and it starts to leave, the magnetic field is still to the right, and now my ring is leaving. So the magnetic field is getting weaker. The flux is equal to B times A. B is getting weaker, so my flux is getting weaker. And so the ring is going to say, oh, the magnetic flux is getting less. The flux is getting less. I need to increase the flux. So it is going to make the magnetic field in the same direction as the magnetic field is losing. And so if we then put our fingers, our right hand in this way, right, our right hand, our thumb would point along the ring in that direction indicated, and that will give us our direction. So here the magnetic field is getting stronger. When the magnetic field was getting stronger, the ring made a magnetic field to go the opposite direction. And when the magnetic field is getting weaker, it says, no, we can't disappear yet. The magnetic field from the induced current will be in the same direction. So basically you can think of Lenz's law as being kind of stodgy, not liking change. The current will always want to try to maintain the status quo and always try to make a magnetic field that makes the magnetic field stay the same, makes the flux stay the same. It opposes change. So what does it mean that we are looking at an induced current opposing the change in magnetic flux? So magnetic flux is, again, I is equal to B times A times the cosine of theta. So we can change it by changing the angle. And none of these examples here are going to look at the angle change. We're going to look primarily at B and A. So here we have a ring that we're changing the area of it. And so the basically the magnetic flux is getting weaker because the area is getting smaller. So here we say area is getting smaller. So the flux is getting smaller. and the induced magnetic field will want to oppose that change. So it wants to basically bring back some magnetic field going in the same direction as the current magnetic field because it's losing it and it wants to bring it back. It's like, oh, it's going away. I can't stand it going away. So it will create magnetic field lines in the same direction. And so to figure out what direction it goes, I like to have a loop handy. So you can either use an actual loop of wire, a hula hoop, a hair thing, anything that you have that's a ring. But I highly suggest getting a ring of some sort, a ring of tape, some sort of ring. And so here, to get the magnetic field lines to go out towards me, indicated by the dots, then I'm going to hold the loop with my fingers pointing on the inside, and the direction of my thumb is the direction of the current. So in this case, the current is going to want to go counterclockwise. So the current will move counterclockwise through this bar and all around as it's creating the magnetic field in. Then we're going to look at the next loop, and the next loop is leaving the magnetic field. And leaving the magnetic field will mean that once it leaves, it's also losing that precious, precious magnetic field. It's disappearing because it's leaving, and so it wants to bring it back. So again, the lines are out towards me, and so I'm going to want to make a magnetic field with lines pointed out towards me. My thumb is pointed to the right when I'm holding it on the bottom. It's pointed to the left when I'm holding it on the top. And so I get magnetic field lines out. So this is counterclockwise, this is counterclockwise. Now we're leaving the magnetic, we're entering the magnetic field. So we're going from an area with no magnetic field to an area with magnetic field. So we said this is B's decreasing. So my magnetic flux is decreasing. Now we're going to say my magnetic flux is increasing because B is increasing. So flux is increasing, and it's going to say, magnetic field? No, I don't do magnetic fields. Who said we were doing magnetic fields? And so it's going to try to oppose that change. So always do the opposite. It's just a difficult loop. It always needs to do the opposite, and so the magnetic fields will be in this time. And to create that, I grab my loop again. But now I have my fingers pointed in, and so that means my thumb is going to the left at the bottom and to the right at the top, depending on which way I hold it. And so here we get a clockwise magnetic field. And this one, the bar is moving to the right. The magnetic field lines are pointing in. It says, no, we don't do more magnetic field lines. We just got used to the old ones. So it is again going to oppose the change and create magnetic field lines going in, and we said that was clockwise. Okay, so far we've just been changing the B, and that's changing the flux. And so here we're also going to be changing the B. And so here my magnetic field is increasing, presumably in the same direction. It's going to want to oppose that change, so the magnetic field lines will be into the page. So again, I grab this loop with my magnetic fields pointing into the page. And so we're going in a clockwise direction again. So this is clockwise, and if B is decreasing, then it's going to say, no, don't leave. We want to create magnetic field lines coming out towards us. Again, out towards us, we grab the loop, we put the hand out towards us. The thumb at the bottom is going to the right, thumb at the top is going to the left. That means we are going in a counterclockwise fashion. So counterclockwise. Here's all those explanations written up. Hopefully they make sense. We will certainly get more practice on this. So here's an example for you to think about. So here we have a loop, and it's traversing from an area with no magnetic field into an area with a magnetic field as it moves across the screen. So here the magnetic flux is 0, and so there's nothing going on. There is no current and no direction of current whatsoever. So there's no current. Nothing about what happens as it moves into and then through this magnetic field, and fill out the answers. Okay, at point B, the magnetic field, it says, is coming out. I've attempted to put dots in there. And so the magnetic field is coming out. That means B is getting stronger. The area presumably stays the same, so that means the flux is increasing. The induced magnetic field will want to decrease the flux and therefore decrease the magnetic field. To decrease the magnetic field, it needs to create an opposing magnetic field. To create the opposing magnetic field, it needs to have a magnetic field that's in. So we get our handy dandy loop out again, put our fingers into the loop to represent the magnetic field going away from us, and we'll find that our fingers, a thumb at the bottom is pointed to the left, at the top it's pointing towards the right, and so we would call this a clockwise fashion. And then in the middle here, the change in flux is 0. So the change in flux is equal to 0. So the current is equal to 0. So no current there as well. And then as we're leaving, the magnetic field is still pointing out at us. It says, oh, I just got used to this magnetic field. You can't leave me now. And so it's going to attempt to oppose that change. And so it's going to also make a magnetic field coming out towards us. And to make a magnetic field coming out towards us, we can grab our loop with our fingers out towards us, moving now counterclockwise around. So the induced current will be in a counterclockwise direction as we move around.